In the previous video, we covered the layout and essential properties used to define an AptPlot step. Now let's apply the information we know to define an AptPlot step within 3 different job submissions. The following examples will show how to create 2 graphs representing data from a pipe within a trace restart case, create an axial plot within a tabular parametric job stream, as well as define and submit an AptPlot batch submission to the calculation server. All of the files needed for this exercise can be downloaded by clicking the AptPlot exercise link in the description. We'll start by opening the standpipe basic model defined within the downloaded exercises folder. Expand the JobStreams node within the navigator and define a new AptPlot step within the standpipe stream. Let's name our step sample plot and drag it from the navigator and place it to the right of the standpipe restart case provided in the view. It's important to note that the step has only one input, an optional input labeled param that represents the parameter file property. Plot file inputs are not enabled by default, as AptPlot can open any number of files from a wide range of file types. An AptPlot step must define its inputs explicitly. Select the parameter file checkbox if it is not already checked and press the Properties selection button. Open the 2graphs.par file that is provided with the exercise. Once the 2graphs file has been opened, a new external file will be created in the stream representing the parameter file and will be connected to the optional param input on the sample plot step. This parameter file will be used by default for all plots that do not explicitly define their own parameter file. Once the 2graphs file has been opened, a new external file will be created in the stream representing the parameter file and will be connected to the optional param input on the sample plot step. Expand the Files category under the standpipe stream and drag external file 1 from the navigator into the view, just above the standpipe restart case. Our view for the job submission process is now complete. Next, let's navigate to the sample plot step we defined earlier and edit the plot inputs. Create a new input and provide the information needed for a valid input. We'll name our input xtvin and define the type as trace. Note that once created, the new input has now appeared on the AptPlot step with the name we set as its label. Connect the xtv output of the standpipe restart step to the input of the AptPlot step. Now that the input file has been defined in the plot step, let's start by adding the top graph to the plot. This graph shows a comparison plot of the pressure in the first and last cells in pipe 2. Navigate to the Plots dialog and expand the Plot 1 node in the tree. Select the first graph defined and set the title and subtitle to some appropriate names and create a new data set. Within the new data set, set the input to the plot input defined earlier. Set the dependent data to PN2A01. This is the trace analysis code plot channel name for the pressure of pipe 2 in the first axial cell. This tells the AptPlot what plot channel for the dependent, or y-axis, of the dataset. Set the legend entry to pressure 2A01. Click on the graph and create another data set and set the input to the previously defined plot input, the dependent data to PN2A20, and the legend entry to pressure 2A20. For this graph, leave the display properties for the data sets to the default. This will result in lines with no symbols but different colors. Now let's create the second graph that shows the density of liquid in the first axial cell of pipe 2. Select P0 and create a new graph. In the new graph, create a new data set and set the input to the xtvin file. Set the dependent data set to ROVN2A01 and legend entry to density 2A01. Close the Plots dialog and navigate to the Plot Outputs dialog. Create a new output and select P0 as its plot. All outputs on an AptPlot step are specific to a single plot. Assign a name to the output and set the type to a PNG file. Create another output and assign a name and the plot from the plot inputs. For the type, select the AptPlot file option and close the dialog. With this output setup, we will have two generated output files, one PNG image and one APF file, which is AptPlot's native file format representing P0. Now let's submit our stream to the calculation server by right-clicking the standpipe stream and selecting the Submit Stream to Local option. Once our jobs have completed successfully, we can now view the results of a run and view our AptPlot submission. To do this, select the sample plot in the table and view its output files. Out of the available options, select Images and then select the generated image from Output. The previous example showed a very basic understanding of how to define an AptPlot step within a job stream. Now let's take it a step further and create an AptPlot step with a tabular parametric job stream. This video assumes you have a basic understanding of snap variables and tabular parametrics, and will instead focus on the AptPlot job step creation within a parametric job stream. Open the AptPlot or parametric stream model that is provided in the link below. Expand the job streams category and select the tabular parametric job stream. Create a new AptPlot step and name it Void Profile. Open the Plot Inputs editor and define an input for our AptPlot stream step. Set the name of the input as xtvin and set the type to trace. In addition to setting the name and type, we will also set the file set to true to enable multiple files for our single execution of the job step. Drag the AptPlot step into the single step view and connect the trace output to the input of the step using the connection tool. Our configuration for the input is now set. Navigate to the Plots dialog and define the attributes and datasets of our graph. Once the Plots dialog is open, set the following properties on G0. Create a new dataset for G0 and set the input to our previously defined input. Set the following properties on sets 0 through 5. Next, we'll embed the parametric keywords directly into the text of a plot. This will allow the legend entries to identify the input values associated with a particular dataset. To embed these values, wrap the replacement with braces preceded with a $sign. Inside the braces, we identify a parametric keyword value with the prefix pkwv, followed by a colon. After the colon, identify the parametric keyword by name. The provided example will be replaced with the inlet velocity variable. Now set the legend entry to the following text. Close the Plots dialog and navigate to the Plot Outputs dialog. Create a new output and select the plot we have defined within the Plots dialog. Name the output to Void Profile and set the type to PDF. Once our output has been configured, we can now submit our job to the calculation server. Finally, let's view our results from the submission and verify we have generated the necessary data. For our final example, we'll cover the usage of an AptPlot batch submission for an interactive stream using two different input sources. Using AptPlot, we will model the behavior between the void fraction value of a steady state and transient stream using the elevation of a pipe as our independent data. We will also introduce some common commands used within AptPlot batch submissions in order to generate plots. You can find the full suite of commands by looking in the AptPlot User's Manual and navigating to the Scripting section. Let's get started by opening the AptPlot batch model, included with the exercises within the AptPlot batch folder. It's important to leave the other files in this folder alone, as they will be used later in the exercise. Once the model has been opened, let's navigate to the defined interactive stream and select the AptPlot step included with the stream steps. Open the script editor within the Properties view. We'll use this editor to explore our script and define our two inputs for our plot data. Click on Import and select the script.b file included with the AptPlot batch folder. First, replace the path value defined on the third line with the path to the locally downloaded AptPlot batch folder. Now that our script is set up correctly, let's take a look at the commands we'll use to create our plot. First, we have the track and xtv commands that are used to open a specified file type. In our example, we use the track command to open the xtv files generated from the steady state and transient steps. The 0 and 1 are used to internally signify which input file is which during the execution of the submission. These values are important if the user wants to use more than one input within their submission, but are not needed if only one input is used. Lastly, we have the names defined for the inputs. These names are surrounded with curly brackets and a prepended $, so they can be tokenized and represented as the names of the individual inputs for the submission. Next, we have the getP command responsible for grabbing the parameter file for the graph. This file will enhance the look of our graph so we can see the differentiation in the various data we have. The next three groups of commands use the calc command to evaluate a user-defined equation containing a function, operator, or symbolic variable. The first grabs some values at 120 seconds from the specified channel pattern, with the %2n indicating that a channel index shall be substituted into that portion of the pattern, with at least 2 digits used to represent the index. With our example, we have a vector named elevations that will grab the x positions within a heat structure to plot its axial positions. Our next group of calc commands grab the void fraction values from the data within the elevations vector. Notice how within the supplied channel patterns, we have the void 1 value set to T0, which in our case represents the first input file named xtv in SS. We will grab the void fraction values along the entirety of pipe 2's length at the very ending of our steady state operation. We will then use T1 or xtv in TR to grab the void fraction values along the entirety of pipe 2's length at various times throughout the accident. Our final group of calc commands will swap the x and y axis values so that the elevation values are on the vertical axis. Using the plotvar command, we add our data to the current plot and use the following 4 commands to set titles and legend entries. We must redraw the table to ensure we have all the latest commands applied to the plot, set the output result of the file to a PDF, and print to the output image defined in the plot outputs. Notice that like the input file, the print command includes a replacement token. This is used to tell the AptPlot batch step to create an output file token. This allows the output of this step to be used downstream or to be cached using the output file storage capabilities of any job step. Press OK on the script editor, drag the AptPlot step into the interactive stream view, and connect the transient and steady state steps to their respective inputs on the AptPlot batch step. Submit the stream and wait for the submission to complete within the JobStream console. Navigate to the AptPlot step related to the submission and view its generated file.